Good evening and good morning, everyone. My name is Chin Chen. I'm a professor of ophthalmology at the National University of Singapore. I'm also the director of the Center for Innovation and Precision Eye Health. On behalf of the center, it's my great pleasure to welcome all of you to this Innovation and Precision Eye Health webinar series. The purpose of this series is to provide new insight on the latest scientific advance in the understanding and measurement of eye disease. We have invited leading local and international clinician scientists, and policymakers to share and debate their perspective on the digitalization and precision of eye care in Singapore and around the world. Today, we are very glad to have Professor Piers Keynes with us in this webinar. Professor Keynes is a professor of artificial medical intelligence at the University College London and a consultant ophthalmologist at the Moorfields Eye Hospitals. In 2016, he initiated a cooperation between Moorfields and Google, and this cooperation has led to many high-impact publications, including at least 2 papers in Nature Medicine. He has many honors, including the Evening Standard Progress 1000 list of most influential Londoners and the top 10 of the power list by the Ophthalmologist magazines, and many others. Before Professor Keynes' talk, I would like to remind the audience that basically all of the participants are muted. So if you have any comment and questions, you are welcome to post them on the Q&A sessions. Now, without further ado, may I invite Professor Piers Keynes to give his talk. Piers, over to you. Thank you.
Thank you, Professor Cheng, for the very nice introduction. And I only wish that I was able to be giving this talk in person in Singapore, but hopefully we'll be able to do that in the near future. So I'm just going to share my screen. And so over the next 40 minutes, I'm really excited to talk about transforming healthcare with artificial intelligence and pass on some of the lessons I think that we've learned from ophthalmology. And one of the things that I firmly believe is that ophthalmology is one of the medical specialties that is at the forefront of AI-enabled healthcare, and in fact can be an exemplar for other medical specialties. Now, one of the things that I always like to do when I give a talk is include my contact details. So for those who'd like to follow me on Twitter, I've included my Twitter handle in the bottom right of this slide. And on the last email of the presentation, on the last slide of the presentation, I'll give my email address if people would prefer to get in touch with me via that road. So Professor Cheng has already said a little bit about me, but just to reiterate, I'm a consultant ophthalmologist at Moorfields Eye Hospital in London. And at Moorfields, I work in the medical retina service. So I specialize in the treatment of conditions like age-related macular degeneration and diabetic eye disease. I'm also a professor of artificial medical intelligence at University College London. And although I'm not a computer scientist or not an engineer, I'm a clinician, a clinical academic. I've somehow come to find myself leading a multidisciplinary clinical research group that aims to develop and apply artificial intelligence in healthcare. And as I've said, we use ophthalmology as an exemplar for the medical specialties in this regard. Now, I'm also very fortunate that I'm funded by UK Research and Innovation. And I'm actually not originally from the UK. I'm originally from Ireland. And the reason that I came to the UK was because of the funding opportunities that they had for clinical academics. And that allowed me to combine my clinical development with my academic development. And so currently, for example, I spend 1 day a week doing retina clinics, and the other 80% of my time is spent doing research. And that's not something that would have been possible for me back in Ireland, or it would have certainly been more difficult. Now, in this talk, I thought I'd tell you about 3 areas that I'm really excited about. So the first is, I thought I'd tell you a little bit about what are called foundation models and how foundation models are getting everybody very excited outside healthcare, and how we're going to start to see foundation models in healthcare very soon, if not already, and how that is going to fundamentally change some of the practices around the way that we use data in AI-enabled healthcare in the future. So the second thing is that I'm going to talk about the collaboration between Moorfields and Deep Mind, and tell you a little bit about what we've done in that collaboration, but also talk a little bit about the challenges of going from code to clinic. And actually, you know, it's one thing to publish a cool research paper, but it's a very difficult and much longer and trickier thing to actually take an algorithm and see it made into a commercially available medical product and used at scale for patient benefit. So I'll tell you a little bit about the way that work is going so far. And then the last thing that I'm going to talk about is something that in Singapore and Asia that you have huge expertise in, but this is the growing field of using the eye as a window to systemic health, something that we call oculomics. And can we take a retinal photograph or an OCT scan and potentially use it as a way to diagnose or to predict some other systemic medical conditions? So, first of all, let me talk about the new era in artificial intelligence that has started to emerge in recent years. So back in 2016, the New York Times referred to the advent of deep learning, which is a type of machine learning, which is a type of artificial intelligence, as the great AI awakening. And it described how all the major technology companies have become AI-first companies. And now in our smartphones that we use on a regular basis, AI is a fundamental part of them. And so that helps us with things like translation between foreign languages, image recognition, speech recognition, and many, many other things. Now, the exciting thing from my perspective is that the progress has been accelerating over the last few years. And so in July of 2022, The Economist had on the front cover about AI's new frontier, and a very, very interesting article inside about how progress in artificial intelligence is accelerating. Also, as a matter of interest, you can see on the cover there, it's also in this particular issue, it has a nice article about the short-sightedness epidemic. And I'm sure that many experts from Asia and from Singapore were quoted in that particular article. So the article about the cover issue is about huge foundation models that are turbocharging AI progress. And a key point is that they can have abilities that their creators did not foresee. And it's from June 11th, 2022. And so foundation models is actually a term that was actually really introduced by a very large group from Stanford back in 2021 in this preprint. And essentially, this is a rebranding of something that has been around for 30 or 40 years, which is essentially pre-training on very large data sets. Now, the key thing is that this has gotten a lot of prominence in two major areas outside healthcare in the past 6 to 12 months. So the first is creation of something called large language models. And most famously, you have ChatGPT from OpenAI, which has gotten a lot of recognition. One of the first big AI systems to reach 100 million users, and it achieved that in a very, very rapid period of time. Now, I give a lot of talks about AI, and generally when I give talks to general audiences, the audiences are not very familiar with the specific AI technologies that I talk about. But I can tell you, when you give a talk now to a general audience of non-experts, non-clinicians, or even of clinicians, almost everybody in the audience will have heard of ChatGPT. And if you go to any high school or any university, you can bet that every student has heard of it. And essentially, this is a model which has been trained on almost all the openly available texts that's out there on the internet. And for those of you who haven't tried it before, I highly encourage you to log into ChatGPT and start to experiment with it. And so, for example, if you're an ophthalmologist, you could ask ChatGPT to write a patient information sheet on age-related macular degeneration, and it would be amazing what it can produce. Or if you wanted to, you could say, write a patient information sheet on age-related macular degeneration in the form of an amusing rhyme or something like that, and it will give you amazingly interesting answers. Now, you've got lots of companies that are beginning to use this, and so this is an article about a company called Character.ai, which has recently raised hundreds of millions of dollars. And essentially, the idea is that they can use these large language models to make a copy of any person, whether alive or dead. So, for example, you might imagine that you're having a conversation with William Shakespeare or Barack Obama or someone like that, all with this technology. And it can be amazingly realistic, the responses that are given. Now, the other area where foundation models have gotten a lot of attention is something called generative AI. And again, OpenAI have gotten a lot of prominence for this because they have something called DALL-E. And again, DALL-E is something that's free to log into, and anybody can set up an account and you can start to generate some of the images that I'm about to show you. But there are a number of other big generative AI platforms that are available. There's something called Midjourney, and there's something called Stable Diffusion. And Stable Diffusion, which is from the UK, is open source. And so it's you can actually use it to generate any type of images that you want. Now with DALL-E, this has gotten a lot of excitement because you can just put in a text prompt and it will generate an image. And so you can go on the internet and you can find lots and lots of interesting images that have been created. And someone put in this: avocados dancing, singing, and partying at a Hawaiian luau, and DALL-E created this image. Or someone put in an Italian town made of pasta, tomatoes, basil, and parmesan, and DALL-E created this image. And in fact, the creative industry has already begun to really adopt this technology. Now, of course, there are fears among the creative industry about, will this put artists and graphic designers out of work? But in fact, they've really begun to adopt it because it does take some creativity to get nice and meaningful images from these. And in fact, it turns out now that more than 20 million images are being created with these systems every single day by people around the world. So it's become a very, very powerful thing. Now, the key aspect about these foundation models is that they're trained on very, very large amounts of data. And they're typically trained using an unsupervised form or something called self-supervised learning. And so this is what facilitates the use of such large amounts of data. For example, billions of words or millions or billions of images or videos, because the previous approaches would often require something called supervised learning, where you would have to label all of the images or all of the text in order to be able to train a model. With self-supervised learning, you generate labels from within the data. And so, for example, if you have text data, you would essentially, you might have a sentence in a paragraph and you would cover some of the words, and then you would train the model to try to guess what the missing words were, and then you would try to optimize for that function. Or on an image, what you might do is cover large parts of the image, and then the model tries to predict what those images are. And it turns out that if you do that, you can train on huge amounts of data. You can then develop this kind of very sophisticated feature representation. And what you can then do is fine-tune the model in specific use cases. And so that can be with much smaller amounts of data, or in some cases with no additional labeling. And that's something called zero-shot learning. So this is very exciting because this might help with rare diseases. So for example, you might have a foundation model trained on millions of retinal images, and you want to fine-tune it to diagnose a rare inherited retinal disease where you only have like 20 examples. And essentially you can fine-tune with that, and you can potentially get pretty good performance in those things. And it wouldn't have been possible with the smaller amounts of data to achieve that prior to this. The other big aspect about these foundation models is that they typically employ a different architecture. So much of the work we've been doing in deep learning over the last decade has been using something called convolutional neural networks. And these are neural networks that are very good for image classification tasks. But in fact, much of what we're doing now with these foundation models is using a new type of architecture called transformers. And these were first applied to large language models back in 2017 in a famous paper from Google called "Attention is All You Need." But more recently, they've also been applied to image data, and that's when they're called vision transformers. Now, the exciting thing about the use of transformers is that they are potentially a very scalable architecture. In other words, it's possible to build models of very large models of very big complexity. And so you now have vision transformer models that have over 22 billion parameters. And in large language models, you have transformers with over half a billion, over half a trillion parameters. And it's likely in the coming year, we're going to see models with 1 trillion or more parameters. And one of the exciting things that we've learned is that if you scale up the amount of data massively, and you scale up the size and complexity of the models, you start to see very powerful and unexpected results. And this is why everybody's got so excited about ChatGPT, because I can tell you the first time you start to use it, it's a really mind-blowing experience. Now, of course, there's lots and lots of cautions about ChatGPT or Bard, which is the Google equivalent, or lots and lots of other things. They'll make up information. They'll have information that superficially looks correct, but is subtly wrong. And so there's lots and lots of issues there, but nonetheless, it's a very exciting area. Now, I think that the power of these foundation models is going to lead to some paradigm shifts around the way that we collect large medical data sets. Because the fact of the matter is that the major limitation in AI in healthcare is that we have only limited access to data sets. And if the data sets are small, for example, less than many millions of images, then it's probably not going to benefit from using vision transformers or some of these approaches. But we're going to see such huge advances outside healthcare that I think it is going to put a lot of pressure on us within healthcare to try and take advantage of the power of these models for patient benefit. And so I think that that's going to be facilitated in a number of ways. So the first is, I think we're going to increasingly move to the cloud for our healthcare data and our healthcare institutions. So in our personal lives, I think most of us now have increasingly moved to the cloud. We, watch TV on Netflix and listen to music on Spotify or equivalents. We store our family photos in the cloud. And increasingly now we're seeing hospitals moving to the cloud. So at Moorfields, we have a cloud-based data platform. We've got big centers like the Mayo Clinic and Stanford and others have moved to the cloud. In the UK, in the National Health Service, the entire blood and transplant service uses Microsoft Azure, and the entire electronic referral system for the country is on Amazon Web Services. So we're increasingly realizing that cloud-based services are potentially more secure, more flexible, more scalable. Now, I'm the director of the Insight Health Data Research Hub, which I'd be happy to take some questions about in the discussion. But this has a cloud-based infrastructure, which has about 25 million images in it. And it's only because of the power of the cloud that we can really take advantage of this. The other thing, apart from the use of the cloud, that I think is going to be really important is privacy-enhancing technologies. And I know that this is some exciting work in this area is being done in Singapore. But in London, in the UK, we've been working with a startup called Bitfound. And they're based just 5 minutes walk away from Moorfields in East London. And Bitfound are a company that specializes in privacy protecting technologies, founded by a South African guy called Blaise Thompson. And Blaise was previously the chief architect for Siri at Apple. And Apple are one of the world leaders in privacy protecting technologies. And for example, when you have messages on your phone in Apple, they can predict which word is going to come next because they've trained models on data from millions of phones using federated learning. So essentially, they can train the models on each individual phone without having to aggregate all of the data. And they also use federated learning for Siri, their voice assistant. And so Blaze was the chief architect for that. And the head of engineering for Bitfount is a guy called Matt Siegel, and he was the person who developed the federated learning platform that Apple used. So, like I say, Bitfount are a small startup just founded in the last couple of years, based in East London. You can see me hiding at the back there on the right. I've been able to work with them for the last couple of years. And essentially, we've been able to deploy their platform at Moorfields and at University College London. And we've been able to show how nicely it can be used to train models using these federated approaches. So these are the things that I think are going to facilitate use of data at scale and thus facilitate foundation models. So a combination of moving our data to the cloud and using privacy protecting technologies such as federated learning. Now, the second thing I'd like to talk about is the work that we've been doing even before the advent of foundation models in ophthalmology with deep learning. Now, of course, we all know that ophthalmology has been one of the medical specialties at the forefront of AI-enabled healthcare. You had the first ever FDA-cleared autonomous AI system was in 2018 when the company IDX got clearance for their diabetic retinopathy software. And the second ever FDA clearance for an autonomous AI system was also for diabetic retinopathy, and that was in August 2020 for the company Inuk. And I know, of course, Singapore and a number of other Asian companies are doing really cutting edge work in terms of diabetic retinopathy screening and other AI applications, and are actually using these systems for widespread patient benefit already. So back in July 2016, I initiated a research collaboration, as Professor Cheng has said, between Moorfields and the artificial intelligence company DeepMind. Now, DeepMind are a company that are founded in 2012 in London. In 2014, they were acquired by Google, reputedly for about £400 million, and they're arguably one of the world's leading artificial intelligence companies. And from my perspective, the exciting thing about them is that they're based just 2 stops away from Moorfields on the London Underground, the Tube. So it takes about 5 to 10 minutes for me to get from Moorfields to their headquarters. The other exciting thing is that Moorfields is building a new hospital in the King's Cross area of London. So we'll actually be 2 minutes walk from the main Google headquarters and the DeepMind headquarters, as well as the main University College campus and a lot of other exciting companies in this area of London, which is called the Knowledge Quarter. So essentially, we've been working with DeepMind since 2015, 2016 to develop a deep learning system that could be applied to OCT scans, macular OCT scans, and could be used by non-experts to triage people with suspected macular disease. So if a person goes to their community optometrist and they have some new onset distortion and the optometrist is worried about wet AMD, for example, then the algorithm would help them to be able to diagnose this and help them to be able to appropriately refer on to a retina specialist to make the diagnosis and give the treatment. Now, in August 2018, we published, as Professor Cheng has said, we published the first results of this in Nature Medicine. You can see that this is over 30 different authors on this paper, and it reflects the fact that this was a real multidisciplinary collaboration. It was featured on the cover of Nature Medicine. And of course, this being AI, you can't escape the hype. And so it was exciting that it got a lot of media attention. Now, it was exciting, but it was also a little bit awkward because the fact of the matter is, although AI has the potential to save the sight of millions of people, in fact, we have not used this algorithm yet, even in 2023, to save the sight of a single person. And so that speaks to some of the challenges I'll tell you about in a few minutes about going from code to clinic. But first, before I do, let me just show you the algorithm in action. So if you look at the bottom row here, we take a macular OCT scan, we feed it into the AI system. There's, first of all, a segmentation network, which is a neural network that's been trained to delineate between 10 and 15 different anatomic parameters on the OCT. And you can see those listed in the bottom right. So in this case, it's delineating intraretinal fluid. And then a second neural network gives a referral suggestion, which you can see in the top left, and also gives a diagnosis probability. So in this case, the algorithm is recommending semi-urgent referral to see a retina specialist, and it's diagnosing macular retinal edema. So it works for more than 50 different retinal diseases. So here's an example of a patient with age-related macular degeneration. So if you look at the OCT on the left, on the bottom row, you can see this, choroidal neovascularization coming from under the retina. On the third row, you can see in reddish orange fibrovascular pigment epithelium detachment. On the second row, you can see subretinal fluid around the fibrovascular PED. And in the top left, you can see the algorithm is recommending urgent referral and giving a diagnosis of choroidal neovascularization with 99.5% certainty. So, as I said, this is AI, and so it's exciting that the work was able to get global media attention. We had the Prime Minister of our country at the time talking about it to the CEO of IBM at the Bloomberg Global Business Forum in New York. And then a real career highlight for me was we were able to do a live demonstration of the algorithm at the BBC Royal Institution Christmas Lectures, which is a very big event that occurs every Christmas in the United Kingdom for more than 100 years. And so we were able to bring in a TopCon OCT and connect it up. We got a patient from Moorfields with wet AMD called Elaine Manna, and we did a live demonstration in front of 200 or 300 kids in the audience for the BBC Christmas lectures. Now, we're also quite proud that we have spent a lot of time and effort on data protection and ethical approvals, and information governance, and patient and public involvement. And because the thing to remember is that this collaboration involved sharing over 1 million OCT scans, anonymized retrospective scans, with an industry partner, which was DeepMind. And you can imagine the sensitivities of sharing with a company when it's data from the public health system, but also when the parent company is Google or Alphabet. And so we're very proud that we've done everything we think as to a high standard in this regard. And so what was interesting, in August of 2022, there was an article in the Telegraph newspaper in the UK about Google being sued for work they did with a different hospital, the Royal Free Hospital, around acute kidney injury. So this work is not related to the work between Moorfields and DeepMind. And I don't know whether this is a valid legal case or not. But what was exciting for me was that when we read the last part of the article, there was a quote from a guy called Phil Booth, who is a person who's a real expert in data protection and is part of a patient privacy group called Med Confidential. And he said, it's perfectly possible to carry out open, ethical, responsible science and health research that has real benefits, such as when DeepMind partnered with Moorfields Eye Hospital. And so just to highlight that it is possible to work between academia and industry and do things right in terms of many of these areas. Now, of course, we're not resting on our laurels in that regard, and we're always trying to improve and get better and make sure we continue to do things right. Now, where are we then in 2023 with this? Well, I'd like to tell a story about Ken Cukier. Ken is a senior editor at The Economist who had written about our work before, so was familiar with it. And in March 2021, he developed sudden vision loss in his left eye, and he emailed me on a Saturday. I think we were in the middle of a lockdown in the UK at the time. So I immediately gave him a call, and I was able to give him advice about going into the Moorfields emergency department and getting seen and getting treated. And so when he went into the emergency department and the nurse was checking his vision, the first thing he asked the nurse was, where's the AI system that's going to diagnose me? And the nurse looked at him like he was crazy. And then he went to the doctor and he said, where's the AI system? And the doctor looked at him like he was crazy. And so a few days after he was seen and treated in Moorfields, he posted this tweet where he said, very gently teasing us, where he said, AI is a fraud. I went to Moorfields for emergency eye surgery. Instead of DeepMind's cool algorithms diagnosing me and robot surgeons, I had to accept the excellent skill, thoughtful care of human medical staff. What a disappointment. Now, actually, the condition he had was not something that you would diagnose with macular OCT. And so the AI system wouldn't have worked, but he nonetheless raised a very valid point. When you've got all this hype around AI, and a few years later, the AI system is not actually being used in clinical care. And he invited me to come on his podcast called Babbage to speak about this journey of going from code to clinic. So in fact, there are multiple challenges. And so I think everybody knows some of the challenges, but one of them is around clinical validation. And it's relatively easy to publish a paper on retrospective data where you show good results, but actually, can you show that the algorithm will also work? If it's trained on data from white Irish people in London, will it also work on people in Singapore or people in Ghana or people with AMD in Brazil or diabetes in Canada or something like that? And then closely aligned to that is the need for regulatory approval. And so we know that actually getting something like FDA clearance is a huge undertaking, requires many millions of dollars of resources, of funding, plus also extended period of time, plus also quite a bit of specialized expertise to be able to get that or other regulatory approval. Now, however, what I think is becoming increasingly clear is that those are the known challenges, but actually the really gnarly challenges, the really kind of tricky things are going to be about how you integrate the AI systems and deliver them. So how are you going to integrate them with electronic health records or imaging manufacturers, or are you not going to integrate them? And what are the business models associated? So if you have something that can provide a fluid measurement for retina specialists, that might be helpful, but will the retina specialist pay, $15 every time they want to get this measurement? And, how will this be integrated into pathways? If it involves sending data to the cloud and people have to wait for 5 minutes to get the results, will that cause delays in the pathways that mean it's not really viable for use? So these are the sort of challenges we need to circumvent. And so, so for me, the analogy that I like to draw is with the dawning of the electrical age. And I've been reading an awful lot about Thomas Edison over the last year. I've read over 1,000 pages about Thomas Edison, and in particular talking about the dawning of the electrical age. And so people talk about on September 4th, 1882 was the dawn of the electrical age. And that was when Thomas Edison's illuminating company flipped a switch on a power station in New York, and they lit up all of the Pearl Street district of Lower Manhattan. And so what Thomas Edison realized was that it's not just about creating a prototype light bulb, that actually you need to have a reliable source of electricity, you need to have a distribution system, you need to have a connection system, you need to have some sort of measurement system. And so it requires a network of innovations to be actually able to deliver electricity. And at the moment, I think with AI and healthcare, we're a little bit like the light bulbs before 1882, when inventors can show a prototype light bulb and they can show it lighting for a few minutes, but they don't have this network around it that allows it to be distributed and allows it to be integrated and to deliver for care. But I think that we're going to see a lot more of that in the coming years, particularly as we move towards the cloud for our use of our IT infrastructure. So it's exciting to think about what the clinic of 2030 is going to look like. At Moorfields, I've already mentioned, we're building a new hospital. It should be finished in 2027. We're already wanting to make sure we have flexibility in the design of the hospital to take advantage of the new pathways of care that we think AI is going to allow. But really what excites me even more than that is the idea that we can use AI systems to bring specialized expertise out of specialized centers such as Moorfields into the community and maybe into the homes of patients in the future. So in the last 5 minutes, 6 minutes or so, I'm just going to very quickly talk about some work that has come from this in this space called oculomics. And before I do, just to say, both the work that I've just described and the work in oculomics, I think, is going to be greatly facilitated by the fact that OCT imaging is now available widely in the community settings, in community optometrists in many countries around the world. So the key learnings from the Moorfields-Deep Mind collaboration was that we developed the infrastructure to aggregate and curate our data, and we developed a lot of expertise in information governance. And so from this, we began to explore this idea that we can use the eye as a window to the rest of the body, that we can look at a retinal photograph, and with deep learning, we can say whether it's a man or a woman, we can give an estimate of age, we can say whether the patient smokes or not, we can predict whether they're diabetic or not, and we can even potentially measure their blood pressure or give an estimate of their blood pressure or their body mass index. And so my colleague Alistair Denniston, who's a professor in Birmingham in the UK, described the combination of advanced retinal imaging with big data and AI as oculomics. And we wrote a review article about that in TVST in 2020. And so it makes sense that the eye could be a perfect window to systemic health because it's microvasculature that we can directly visualize, and we can look at part of the central nervous system, the retina, with micron level resolution using OCT. And of course, this is building on the work of many others, particularly in Singapore and Australia, where there's many papers that have looked at the cardiovascular associations from eye examinations. But increasingly in recent years, we're seeing links with neurodegenerative disease. And so I'd highlight this paper from the Rotterdam study in JAMA Neurology in 2018. And effectively, what they said was that a thinned retinal nerve fiber layer was associated with increased risk of dementia, including Alzheimer's disease. And they speculated that this could be a preclinical biomarker for dementia. Now, one of the limitations of that study in JAMA Neurology was, I think that involved only about 80 incident cases of dementia. And so in general, the problem with these epidemiological cohort studies is that they're expensive, small number of positive cases. Sometimes they can be sociodemographically homogeneous, and they often lack detailed ophthalmic assessment. And so to address this, we created something called the AlzEye study, where we've linked all patients over the age of 40 years who have had ophthalmic imaging at Moorfields over a 10-year period with a national database in the UK called Hospital Episode Statistics. So we now know everybody who's had this imaging during this time period at Moorfields, if they've gone to a different part of the country and had a heart attack or a stroke or developed Huntington's disease or Parkinson's or multiple sclerosis or thousands of other systemic conditions. So we reported our cohort profile in BMJ Open in 2022 and the processes that we did to make this linkage. And so just to tell you some initial numbers. So for our initial cohort, it's about 350,000 patients, 1.3 million linked hospital admissions. And for our initial data set is about 6.3 million scans. And in terms of systemic disease, we have about 10,000 incident cases of ischemic stroke, whereas in the UK Biobank, we have about 700 patients with retinal imaging who have incident stroke. We have about 12,000 incident cases of myocardial infarction, versus about 1,000 in UK Biobank, and about 13,000 incident cases of dementia versus about 250 in UK Biobank with retinal imaging. So we have potentially huge numbers from accessing routinely collected data. But we also have lots and lots of other conditions as well. Schizophrenia, multiple sclerosis, Huntington's, and lots of other things. In terms of our imaging, we focused on the TopCon imaging initially, although we're going to start to evaluate our Heidelberg imaging soon. We have about 1.8 million color fundus photographs, 1.4 million OCT volumes. And the interesting thing from my perspective is that the funding for UK Biobank is about £250 million. But by comparison, the AlzEye study was funded by a grant for £15,000. And that was from Fight for Sight and Alzheimer's Research UK. And so I call it Biobank on a shoestring, because essentially we were gathering and linking together existing data. Now, what I haven't told you is that it took us 4 years to get the permission to make this linkage. And it's taken us another year to aggregate and process the data. So it's only just in the last 6 months that we're starting to actually do some science with this. So the next step is we're also going to update our permissions so that it's continuously updating. We're going to link with primary care. and we're going to try and extend to different parts of the country. And then we're really interested in how we can explore widespread use through technologies such as federated learning. But even before that, if there are other people that are developing algorithms in other parts of the world and they want to validate on our data sets, externally validate on our data sets, then that's something that we're very, very supportive of. And one of the things just to highlight is, although I've made some criticisms of these epidemiological studies, the fact is that AlzEye has lots of methodological weaknesses as well, even though we have large data sets. And in particular, these are patients that are attending an eye hospital to have scans done. So it's already a biased cohort in that regard. But what I think is exciting is how we can combine really beautiful prospective epidemiological studies with large routinely collected studies, so we can take advantage of the strengths and reduce the weaknesses of each of those. That's one of the things that I'm really keen to do in the future. So it's all about bringing expertise into the community. I think that this could be a game changer, because in the United Kingdom, when you turn 40, you get a text message on your phone asking you to attend your family doctor for a cardiovascular health check, but only 9% of people do it. However, about 80% of people go for an eye test at their local optician during that time. So if we could diagnose systemic disease, or even flag it, potential systemic disease for others to diagnose, then I think that that could have very powerful public health implications in the future. So just to finish my last slide, I know I've already gone a little bit over time. I'm very proud that one of my mentors is Dr. Eric Topol in the United States. And he's written a book called Deep Medicine about how AI can make healthcare human again. And what's exciting for me is that there's quite a nice section on AI and ophthalmology in this book. And he always praises ophthalmology as being one of the medical specialties at the forefront of this. And so I was able to work with Dr. Topol in 2019, and we wrote an essay together called Reinventing the Eye Exam in the Lancet, which sets out in a little bit more detail some of the things that I've talked about. But really, I do believe that despite the hype around this technology, it is going to lead to exciting transformations in healthcare, and particularly in ophthalmology in the coming years. And then lastly, as promised, that's my email address. Thank you very much.
Thank you, Piers. I mean, your talk is very informative, educational, and inspiring. Now, may I invite Dr. Max Tan from National University Hospital to join the panel discussion. Dr. Tan is the Deputy Group CTO of the National University Health System, and he has been, helping to setting up the data set for the entire hospitals. Marcus.
Thank you, Professor Cheng. Thank you, Professor Keen, for that insightful and exciting talk. I really liked your analogy of the dawn of the electrical age with our current state of AI. It takes a series of innovative changes in infrastructure, integration, and delivery to facilitate a transformative change in clinical practice. I would just like to ask you, where do you see the first large-scale application of AI in clinical ophthalmology, and how long do you think it will take for us to get there?
Well, maybe we're already starting to see it, because we do have a number of systems that do diabetic retinopathy screening, and those are now being used at a reasonable scale, although I think they've yet to be really rolled out in millions and millions of patients on a global scale. So I think that is the first thing. I think the second thing is there's a number of startups that are doing fluid segmentation on OCT scans with an aim to help retina specialists. But it's not clear to me how easy it will be for that to be integrated, and whether the business models will make sense for that. So to really answer your question, I think the next thing that's likely to be big is clinical trial recruitment. And part of the reason I think that is because it's going to it might not require regulatory approval. And so let me be more specific. If we have deep learning systems, for example, suppose you have a clinical trial for geographic atrophy due to AMD, you could train a deep learning system to evaluate, to detect and quantify geographic atrophy on Heidelberg OCT scans. And you could potentially put in the inclusion-exclusion criteria of a trial, and then you could potentially run that algorithm on, you could go to a trial site in Singapore and run the algorithm on the entire Heidelberg database or the entire TopCon or the entire Zeiss database, whatever it is. And the algorithm will tell you how many people could be suitable for entry into the trial. And that's going to be really powerful for feasibility planning for trials and for pre-screening of trials. Now, the only caveat, sorry, this is an extended answer, but the only caveat is that I think the only way that that can happen is if it's done locally at the trial sites. I don't think it's going to be possible, like in Singapore. I think it's unlikely you're going to want to say, send all of your Heidelberg database to somebody else's cloud to be analyzed. And so part of the reason I've been working with Bitfound is because it's not just federated learning, it's about federated deployment. So can we actually deploy algorithms locally for clinical trial recruitment in such a way that data never leaves the trial site, and also in such a way that there's no potential leakage of patient data and no potential leakage of intellectual property from the AI systems as well.
Thank you for that. That's very insightful. We are also, having the same issues over here at UH, and the way we do it is very similar to what you've mentioned. We have a sandbox where we have institutions come in, deploy their models, but not take any data out. The other question related to this really would be, given your extensive experience in working with companies like Bitfound and DeepMind, what advice do you have for public health institutions who are looking to partner with private corporations in terms of data governance and security?
Wow, that's a really complex. That's like a 2-hour long conversation just to begin to scratch the surface. One bit of advice I would say, maybe for researchers, is I think that the collaboration with DeepMind was so successful because Demis Hassabis, the founder of DeepMind, and the team working for him, they are most interested in the science and most interested in doing cool research. And that's a very different interaction than if you're interacting with a company where you're interacting with the sales team or the business development team of the company. And so you somehow have to make a judgment about what type of interaction you're having with the company as well.
Yeah, I agree. I think the strategic alignment of all parties has to be very harmonized.
Yeah.
So work out. Yeah, great. Thank you.
Okay, we have a few questions in the Q&A sessions. So the first question is that could Professor Kim highlight some future clinical pathway where AI might play a big role in the communities?
Yeah, so there are a number of companies that have home OCT devices in development. And it seems very likely that if people are going to use those home OCT devices, they will need to have some AI running to be able to automatically analyze and decide when patients need to be referred back in. So I think that that's the first thing. I think the other thing is, as I've been saying in my talk, the community optometry setting, when people are getting their eye test done or people are buying new glasses, I think that increasingly we're going to have screening for eye disease and screening for systemic disease that occurs in that setting. And then lastly, in terms of clinical trial recruitment, imagine if we have clinical trials for early AMD, and those are patients that are often in the community, they're often not necessarily being followed by retina specialists because there isn't any treatment, that actually AI systems will help identify people with early or intermediate AMD in the community for recruitment into clinical trials.
Okay, thanks, Piers. So the second question is that what challenges would you anticipate when using a similar model using Moorfields compared to using Singapore populations?
Yeah. So I think the bottom line is that what we've been doing in AI for the last 10 years usually doesn't really work if you try to apply it in populations that are different from what it's been trained on. If people ask the question, will it work in a Singaporean population? Probably the answer is no, until proven otherwise. Now that may be less of an issue with OCT, but it's certainly a massive issue with retinal fundus photographs. I hope that becomes less of an issue when we move towards foundation models that have been trained on massive data sets, and it seems likely that those will generalize better to different populations with only a small amount of local, retraining.
The next question is also regarding the clinical deployment. At what stage of accuracy will we have the confidence to use it in the real world settings?
I don't think people really know the answer to that, and I think it's still very case by case basis. So, for example, for diabetic retinopathy screening, we know that the FDA set a certain sensitivity requirement for clearance with that study, and the models cleared that, and now it's beginning to be used. But I think for all other applications, it's going to be a case by case basis, and for some of them, it's very hard to think about. Like if we have an AI system that predicts dementia, what sensitivity or specificity or is going to be required? It's going to be really tricky to figure out the answers to those things.
Yeah, I mean, my personal opinion that at least you want to predict Alzheimer's disease, right? The A-gun have to be at least better than the, by questionnaire. I mean, we have some questionnaire. I mean, almost can get 80%. But the AI have to be better than to have its clinical value.
Yeah, exactly. So maybe the way to think of it is not just about what specific sensitivity or specificity, but how it compares with existing methods. That's a really good point.
Okay, now I would also like to invite Assistant Professor Yi Zhong Tam to join the panel discussion. So basically, Assistant Professor Tam is also, working on the real-world deployment, and he's testing out his AI algorithm in detecting visual impairment in the communities. Yi Zhong.
Thank you. First of all, thank you, Piers, for the wonderful talk. As usual, you hold very high standard. And good to see you again. I cannot agree more, and I resonate with what you mentioned just now, network of innovations to enable the integration and eventual deployment of the algorithm. And coming back to there was one question very nicely put forth just now on the community deployment. And you rightly mentioned about the potential deployment amongst the optometrist network, and which there is a huge one in the UK. I'm just thinking, in order to deploy such algorithms in community, for example, amongst the optometrists, the optometry practices, they will need a certain level of infrastructure, the connectivity, the cloud, and the feedback loop in terms of real world processing time must be feasible, must be within seconds or minutes. So how would you foresee us overcoming those barriers so as to make it more palatable for our optometrist partners to take on this as well?
That's another tricky question.
I'm sorry about that.
No, I love it. But this is the type of question that it would be lovely if I was here and if I was there with you in Singapore and we could just have a beer and talk about this for a few hours. But I think so. I think there's so many challenges there. There's also a lot of funding and political challenges in most countries between optometry and ophthalmology. But then there's the technical and infrastructure challenges. But I think, so on the one hand, I think most practices are going to be much more moving towards the cloud in the future for their IT infrastructure. But even for the ones that are still just an OCT machine, it's not networked locally, it's not connected to the cloud, anything like that. There's still going to be a lot of stuff that we can do with deploying these models on the edge, local versions of these models. And so one of the things that is exciting to me is just the power of things like the Apple Silicon, like the M1 and M2 chips from Apple. So like we know, for example, with some of the algorithms we've deployed, just by connecting a new Mac laptop to the OCT device, you can run an AI system that would take a few minutes. Otherwise, you can run it in 7 seconds and analyze the scans locally with that Apple Silicon. So I feel like that could be an option as well as a bridging measure while we wait for everything to be much more cloud connected.
Okay, we have one more question on the Q&A session. So are deep learning algorithms capable of predicting the progression of neurological disease like Alzheimer's?
I'm not sure. I think we hope that it will be able to, but if I had to bet, I think that we'll be able to detect some signs with a reasonable degree of accuracy, but I don't think it's ever going to be 99% sensitive and 99% specific no matter what we do. There's only so much information that's contained within a retinal photograph or an OCT scan, and it's not going to be a magic bullet to fix everything for these things.
Marcus, you have one other question?
Yes, I have one last question. We know that, in predictive modeling, we often get this trade-off between performance and explainability. So often the best performing models, the deep learning models, are not very explainable. Are foundation models also susceptible to this? And how much emphasis should the clinicians place on the importance of explainable models?
So the short answer is, I think it depends on a use by use basis. I think that there'll be some use cases that require explainability and some that don't. And until we really start to explore that, I don't think we can really confidently say. I think that the foundation models may be better in this regard because essentially they're based, transformers are based on these attention mechanisms that potentially could be more explainable than some of the existing approaches, but that's still very much a research area. So we don't know the answers there.
Hi, Piers. If time allows, we still have 2 minutes. I would like to ask one more question. As Marcus nicely alluded to explainability of AI, and I would say conventionally in our AI papers, we have been using heat maps, saliency maps to illustrate explainability. But in truth, actually, that is not quite the best way because heat maps, for example, GradCam or other heat map methods, they do not quite do the networks justice. They are quite crude. They can't really exactly pinpoint the actual features the network, the model is actually using to do its prediction. So in your mind, moving beyond just heat map, saliency map, what is the future trend in terms of explainability of AI?
Yeah, I'm not sure. I'm not sure is the short answer. I think if I had to bet at the moment, I would say something to do with the attention mechanisms and transformers, but it's not something that I really understand enough about as a clinician yet to be able to speak knowledgeably about it.
Okay, time is almost up. So before we close the webinar, I also like to invite all of you, to join our next webinar on 14th of March. And Professor Jose Polito will deliver a very interesting talk. And I also want to invite the local participants to join our center's officially opening on 25th of March. The opening event will be followed by a half-day scientific conference. And our center is also conducting a series of the workshop and educational courses. And the next education course will be in May, focusing on pediatric refraction and myopia management. With that, I want to thank Piers again, and thank you all of you for your participations. Have a good night and a good day. Thank you very much. Bye-bye.
Thank you, Piers. Bye-bye.